I'll just spend a moment on this next section. 44.8 is geometry. And I think you should go and review how to take areas, perimeters, and generally familiarize yourself with the rules of geometry that you had in your elementary algebra or your college algebra. You know, for example, that if I have a circle and I have an angle theta here, and the circle has a radius r, that this will be an arc length s, and that the arc length s is equal to r times theta. In particular, if I look at the distance all the way around a circle, it's 2 pi r, and the distance all the way around theta is therefore 2 pi. Theta is measured in radians when an entire circle is based upon 2 pi. And we don't use 360 degrees. We can use that. But most of our natural functions and logarithms and everything, our trig functions, sine and cosine, are dependent upon using radians. And that's what we would normally use when we take our exponential versions of those. You should be familiar with area and volume. You should think about geometry. For example, why is it that warm-blooded animals can only be so big? Well, if you look at something like the elephant, the volume is increasing, the mass is increasing as the cube of the radius of the elephant, whereas the surface element is only going as the square of the elephant's skin area. Therefore, at some point, the volume of heat that is achieved by metabolization of the food inside the elephant will generate heat, and that heat can't be expended. So it's very important for the elephant to have huge ears that it can flap and cool itself. Likewise, a dog with its fur coat uses its tongue to breathe in and out cool air and cool its tongue with moisture. So just looking at some of those aspects, you can do an awful lot in understanding that volume is proportional to the cube of the length, and this area is proportional to the square. You should know, for example, a rectangle, how you do its area. If it measures a times b, then it's going to have an area of a times b. And if it's a parallelogram and it has a height a and a width b, then again the area is going to be a times b. That's because we could take this triangle here and move it around to here, and it would exactly fit, filling that up, leaving the bottom part with still a length a, and we've made a rectangle out of it, as long as we use the height. So you should know a parallelogram and how to take the area, and a rectangle, and of course a square is going to be just a squared. A triangle, for example, is going to be 1/2 the base times the height. That's the area of a triangle. And again, what we can do is we could take this triangle here, take it and invert it and put it right here, and it would fit exactly. And again, we would have the base times the height, and this would double it. Since we're going to put this part over here, we originally had 1/2 for the triangle, 1/2 the base times the height. But if you put this over here, you can see the area of this whole rectangle is base times height, but the triangle is only half of it. Therefore, a triangle is 1/2 the base times the height for its area. A circle, the perimeter of the circle is 2 pi r, we've already covered. The area of a circle, very important to remember, the area of a circle is going to be equal to pi r squared. Circumference is equal to pi times r, is equal to 2 pi r. The volume of a circle is equal to, this is for a circle now. Let's see, the area, for a circle we have 2 pi r and pi r squared. Now if we look at a sphere, we can look at the area of a sphere, and the area of a sphere is 4 pi r squared. Whereas the volume of a sphere, this is for a sphere, is 4/3 pi r cubed. One kind of interesting thing that comes from this area of a circle, this pi r squared, is that if I take a circle and then I put another circle right next to it, this circle has a radius r and this circle has the same radius r. Then of course I have an area there, pi r squared here and a pi r squared here, so I have two of those. If I now look at what it would be like to have a circle that's 2 pi r squared, then 2 pi, twice the radius would be pi times 2r quantity squared, which means it's going to be 4 pi r squared. So if the radius is twice as great, then in fact this becomes 4 times as great. Let's draw that circle. The radius is now twice as great. Well, isn't that weird? Because what it's saying is this has an area of pi r squared, pi r squared. The whole area is 4 pi r squared. That means this weird looking shape here, with the little cusps and so forth, has an area of pi r squared. And so does this one down here, in order to make up 4 pi r squared. Likewise, if you have a hose that's twice as great, 4 times as much water goes through it. Not twice as much, because the area, the cross-sectional area of that hose is 4. A cylinder is going to be the area of the bottom of the cylinder, pi r squared, times the height. That gives the volume of a cylinder. And you can review your other formulas for volume and area, and you can figure out what the area of a cylinder is. It's going to be 2 pi r. If I cut this thing and open it up, the distance around will be 2 pi r times the height, 2 pi r h. Now I'd like to tell you something about geometry and dimension that's a little bit more advanced. And this is the kind of thing that will really challenge some of you to think about. You'll notice that length increases as the first power. If I go twice as far, not r, but 2r, another r over here, then when I increase that, the length goes as 2 times r. But if I look at the area, if I take a radius and make it twice as great, then the area goes as pi times r squared. In general, it's going to go, no matter what the figure is, it's going to go the square of r, not just the length of r, or r to the first power. The volume of something like a sphere will go as r cubed. So in general, if I increase the general dimension of some other object, the volume will go as the cube. You'll notice that this has to do with the dimension. This is a one-dimensional figure. This is a two-dimensional object and a three-dimensional object. You might guess that if you had a four-dimensional object, then in fact the total content of that object would go as the fourth power of the radius, and that's correct. Now what I would like to explain to you is that there has been a generalization in mathematics of the concept of dimension. You can say, what is dimension? Dimension is the number of numbers needed to give a point, give it to specify. Okay, so in three-dimensional space, x, y, z gives a point. If I'm on an interstate, just the one position will do it because it's one-dimensional. Is it possible to look at fractional dimensions? Well, it really is. Let's suppose that I have a bunch of points that are spread out in some space. It may be one-dimensional, two-dimensional, three-dimensional, whatever. And I take a somewhat central point, and I take a small circle around that point, and I count how many points are inside. So for a given r, I count the number of points. And I find that there are 2 points. For the for a radius of 1, they're 2 points. And then for a radius of 2, which is twice as great, they're 4 points. In fact, what we could do is we could make this on a logarithmic basis, but let's just take it this way for now. And for a radius of 3, they're 9 points. You'd say, well, this is increasing as the square of the number. Therefore, the space is three-dimensional, is two-dimensional, because we're going as the square. In other words, we count how much of the space is increasing as I increase a radius. Well, what if it turned out then that it increased as some fraction? Not as the square, or the first power, the second, or the third, or the fourth, but increased as the 2.315 power. And that's possible. This could increase at some other value like that. Then we would say this space, the points, had a dimension that was fractional. And it turns out that some of the new figures that have been drawn by Mandelbrot, the Mandelbrot sets, and so forth, have fractional dimensionality, like shorelines and other structures like that. And so that's very interesting, and it should Google Mandelbrot and fractional dimension, and you should be able to get some interesting things.